When we look up at the sky every morning, we see a glowing ball of light rising from the horizon. But in reality, that shining sphere is not just a lamp in the sky. It is a star, our sun. The sun sits at the very center of our solar system, holding all the planets, moons, comets, and asteroids in orbit with its powerful gravity. It is the reason Earth is not floating away into the dark void of space. The sun is the closest star to us, and though it may look small from Earth, it is unimaginably huge. Without it, there would be no life, no warmth, and no light. Every drop of energy we use on Earth, whether from plants, animals, wind, or fossil fuels, ultimately comes from the sun's energy. It gives us day and night, seasons, and the cycle of life itself. For billions of years, civilizations have worshipped, studied, and relied on the sun. From ancient temples built to track its movements, to modern observatories that study its mysteries, the sun has always been at the center of human existence. Truly, the sun is not just a star, it is our star. At first glance, the sun looks like a perfect golden circle in the sky. But in reality, its shape is not perfectly round. Because the sun rotates, it bulges slightly at the equator. This makes it what scientists call an oblate spheroid, though the difference is tiny, less than 10 kilometers across its vast diameter of about 1.39 million kilometers. Interestingly, the sun rotates faster at the equator, about 25 days, than at its poles, about 35 days. A phenomenon called differential rotation, which also influences its magnetic field. The sun is so massive that it makes up 99.86% of all the mass in our solar system. Everything else, planets, moons, asteroids, and comets, share just a tiny fraction. If you could somehow weigh it, the sun would be about 330,000 times heavier than Earth. Despite this, it is not solid, but a giant ball of plasma. A state of matter hotter than gas, where atoms are stripped of their electrons. Another surprising fact is that the sun's size is not constant. During its 11-year solar cycle, its outer atmosphere expands and contracts ever so slightly. Even its brightness and diameter shift by tiny fractions, too small for us to notice with the naked eye, but significant enough for astronomers to measure. So, while the sun seems unchanging, its shape and size are in subtle motion, reminding us it's a living, dynamic star, not a static ball of fire. Most people know the sun is mainly hydrogen and helium, but its chemical story is far richer and more surprising. Beyond those two elements, the sun carries traces of over 65 other elements, including iron, nickel, carbon, oxygen, neon, and even rare elements like europium and ytterbium. These heavier elements are present only in tiny fractions, yet they play a critical role in shaping the sun's behavior and evolution. One fascinating fact is that the sun contains more oxygen than carbon, making it an oxygen-rich star. This ratio is crucial because it influences the kinds of planets that can form around it. In fact, without this oxygen dominance, Earth might not have developed oceans. Another rarely mentioned detail is the sun metallicity, a term astronomers use for the proportion of elements heavier than helium. Our sun has a relatively high metallicity compared to many stars, which is thought to be why complex, rocky planets like Earth and Mars could form in the first place. Even more surprising, scientists discovered that the sun's surface doesn't reflect its original composition perfectly. Over billions of years, processes such as gravitational settling caused heavier elements to sink deeper inside, meaning the sun's outer layers are slightly less metal-rich than its core. So, while it may appear to be just a glowing ball of hydrogen and helium, the sun is actually a cosmic cauldron of elements, each contributing to the chemistry of life on Earth. The sun may look like a glowing disk, but beneath that light are 6 distinct layers, each with strange and often overlooked features. At the core, nuclear fusion converts hydrogen into helium. Most people know this, but fewer realize that the energy created here takes an astonishing 100,000 to 1 million years to travel outward. The photons are absorbed and re-emitted countless times, essentially taking a random walk before escaping. Next is the radiative zone, where energy moves as radiation. Interestingly, the density here is so extreme that a single cubic meter contains more mass than a mountain of Earth rock. The convective zone above it acts more like boiling soup, with hot plasma rising and cooler plasma sinking. What's less known is that these convective motions generate mysterious helioseismic waves, vibrations that ripple through the entire sun, allowing scientists to listen to its interior, much like earthquakes reveal Earth's inner structure. Then comes the photosphere, the surface we see. Despite looking solid, it's only about 500 kilometers thick, thinner compared to the scale of the sun. Above it lies the chromosphere, famous for its pinkish-red glow during eclipses. Few realize this layer shoots out towering spicules, jets of plasma taller than Earth itself, lasting only minutes. Finally, the corona, oddly hotter than the surface, reaches millions of degrees. Its mystery heating mechanism is still debated, possibly linked to magnetic reconnection or nanoflares too small for telescopes to catch. So, the sun's structure isn't static. It's a restless, layered symphony of plasma, waves, and magnetic storms. The sun is built like an onion, with layers that behave in ways far stranger than most imagine. At its heart lies the core, where nuclear fusion happens. A surprising fact is that the energy produced here doesn't reach the surface instantly. It takes hundreds of thousands of years for a photon to escape, bouncing around in a chaotic, random walk. Surrounding this is the radiative zone, where energy moves as light. Its density is so crushing that a cubic meter of plasma here outweighs Earth's mountains. Above it lies the convective zone, a restless region where hot plasma rises and cool plasma sinks. These motions create helioseismic waves, subtle vibrations that scientists use like ultrasounds to probe the sun's hidden interior. Next comes the photosphere, the thin surface just 500 kilometers thick, yet it's where sunspots and solar flares erupt. Above it glows the chromosphere, shooting out vast plasma spikes called spicules, taller than Earth and lasting only minutes. Finally, the corona blazes at millions of degrees, mysteriously hotter than the surface itself. Many believe tiny, undetectable nanoflares, or magnetic reconnection, fuel this fiery halo. The sun's structure is not static. It's a living, layered engine, constantly shifting and humming with hidden activity. At the heart of the sun lies its true engine, nuclear fusion. Under unimaginable pressure and temperatures of about 15 million degrees Celsius, hydrogen atoms are forced so close together that they merge into helium. This process releases energy according to Einstein's famous equation E is equal mc squared, where tiny amounts of mass are transformed into enormous bursts of energy. But what most people don't realize is that the sun's core isn't a calm furnace. It's more like a quantum dance. Protons, all positively charged, naturally repel each other. Fusion happens only because of a quantum effect called tunneling, which allows particles to slip through barriers they shouldn't overcome. Without this strange rule of physics, the sun would never shine. The sun mainly uses the proton-proton chain reaction, but in larger stars, a different process called the CNO cycle dominates. In fact, traces of the CNO cycle have been detected in our sun, hinting that it's not as simple as once thought. Every second, the sun converts about 600 million tons of hydrogen into helium, releasing energy that eventually becomes the sunlight warming your skin. Yet the sun hardly notices this loss. It has enough fuel to keep burning for billions of years more. The light and heat we feel from the sun seem instant, but the journey of that energy is far from simple. A photon created in the sun's core may spend hundreds of thousands of years bouncing through the dense plasma before finally escaping into space. Once free, however, it races across 150 million kilometers in just 8 minutes and 20 seconds to reach Earth. What's fascinating is that sunlight isn't just white light. It contains the full spectrum: visible, infrared, ultraviolet, and even X-rays. Only a fraction is visible to our eyes. Much of the energy arrives as infrared heat. Without Earth's atmosphere filtering harmful ultraviolet and X-rays, life would never survive. The sun doesn't shine with constant brightness either. Its output varies slightly during the 11-year solar cycle, affecting Earth's climate in subtle ways. Scientists have even discovered that sunlight contains faint oscillations, tiny pulsations caused by vibrations deep within the sun. As for heat, the sun warms Earth unevenly, driving winds, ocean currents, and weather systems. Every breeze or raindrop ultimately traces back to solar energy. In short, the warmth on your skin today began its journey in the sun's heart millions of years ago. Sunspots may look like dark blemishes on the sun's surface, but they are actually regions of intense magnetic activity where temperatures drop to about 3,500 degrees Celsius, cooler than the surrounding surface. Though cooler, they are still far hotter than any furnace on Earth. What many don't know is that sunspots are not random. They follow an 11-year solar cycle, appearing more frequently during solar maximum. This cycle can influence Earth's technology, as strong magnetic storms linked to sunspots can disrupt satellites, GPS, and even power grids. In 1859, a solar storm known as the Carrington event caused telegraph systems worldwide to fail, and experts warn that a modern repeat could cripple our digital infrastructure. Sunspots are also linked to solar flares and coronal mass ejections, CMEs, massive explosions that hurl billions of tons of charged particles into space. When these particles strike Earth's magnetic field, they create the dazzling auroras seen near the poles. Interestingly, records of sunspots date back to ancient China, where observers documented them without telescopes. Modern studies suggest long periods of reduced sunspots, like the Maunder Minimum, 1645 to 1715, may have contributed to Europe's Little Ice Age. Thus, these dark patches are windows into the sun's hidden, restless power. The sun's magnetic field is one of its most mysterious and powerful features. Generated by the movement of charged plasma in the convective zone, this field constantly twists, stretches, and snaps like invisible ropes of energy. Unlike Earth's relatively stable magnetic poles, the sun's magnetic poles flip every 11 years, a dramatic reversal that drives the solar cycle. What many don't realize is that the sun's magnetic field extends far beyond the planets, creating the heliosphere, a bubble of influence that stretches well past Pluto. This invisible shield protects the solar system from much of the deadly cosmic radiation streaming through our galaxy. Without it, life on Earth would face far harsher conditions. When the sun's tangled magnetic lines suddenly reconnect, they unleash solar flares and coronal mass ejections, blasting charged particles into space. These storms can affect satellites, astronauts, and even cause radio blackouts on Earth. Another little-known fact: scientists have detected magnetic ropes and plasma tornadoes swirling on the sun's surface, larger than our planet. These magnetic structures reveal that the sun is not a quiet star, but a boiling, stormy giant, constantly shaping space weather across the solar system. Like all stars, the sun has a life story. Born about 4.6 billion years ago from a vast cloud of gas and dust, it ignited when gravity squeezed its core hot enough for nuclear fusion to begin. Today, it sits in its main sequence phase, steadily fusing hydrogen into helium. What most people don't realize is that the sun is already almost halfway through its life. It has about 5 billion years of fuel left before major changes occur. As hydrogen runs out, the core will contract while the outer layers expand, turning the sun into a red giant. During this stage, it will grow so large that it may engulf Mercury, Venus, and possibly Earth. Later, the sun will shed its outer layers into space, creating a glowing planetary nebula, a cosmic cloud that will enrich the galaxy with elements for new stars and planets. The core that remains will shrink into a white dwarf, a superdense star no larger than Earth, but with nearly half the sun's mass. Eventually, this remnant will cool into a dark, cold black dwarf. Though silent, it will be the final chapter of the star that gave birth to life on Earth. The sun is not just our light source. It is the foundation of everything we know on Earth. Its heat keeps our planet in the narrow habitable zone, where water can remain liquid. Without this balance, Earth would either be a frozen wasteland or a scorched desert. What most people don't realize is that nearly all energy on Earth is solar in origin. Fossil fuels like coal and oil are ancient sunlight stored in plants and animals. Even wind and ocean currents are powered by the sun's uneven heating of Earth's surface. Only geothermal and nuclear energy escape this solar origin. The sun also protects life in an indirect way. Its solar wind carves out the heliosphere, shielding Earth from much of the galaxy's harmful cosmic radiation. Without it, mutation rates and atmospheric erosion could have been far greater, perhaps preventing life from ever flourishing. Interestingly, small variations in the sun's output have historically influenced human civilization. The Maunder Minimum, a period of few sunspots, coincided with Europe's Little Ice Age, altering harvests and economies. So, beyond giving warmth and light, the sun has shaped our environment, our history, and even the very possibility of life itself. For as long as humans have looked up at the sky, the sun has been more than just a star. It has been a symbol of power, life, and even divinity. Ancient Egyptians worshipped Ra, the sun god, while the Aztecs believed their sun deity required human sacrifices to keep shining. Stone monuments like Stonehenge and the pyramids were aligned with solar events, showing how deeply cultures tracked its cycles. What many don't know is that the sun has also shaped timekeeping. Our 24-hour day, 365-day year, and many calendars are based on its path across the sky. Even the word Sunday comes from honoring the sun. Scientifically, the sun has been central to breakthroughs. In 1919, during a solar eclipse, Einstein's theory of general relativity was confirmed when scientists observed starlight bending around the sun's gravity. Today, solar observatories and spacecraft like Parker Solar Probe study it up close, discovering details such as plasma switchbacks and supersonic solar winds. Beyond science, the sun remains an inspiration in art, literature, and religion. It is both a cosmic furnace and a cultural symbol, reminding us that without it, Earth would be cold, dark, and lifeless. The sun is not just a star in our sky. It is the heartbeat of our solar system, the spark of life on Earth, and a cosmic mystery still unfolding. And this is only one story among countless wonders in our universe. If you enjoyed this journey through the secrets of the sun, make sure to like, subscribe, and join me again next time as we explore more fascinating truths about space, science, and beyond. The universe is full of mysteries waiting to be uncovered, and together we'll keep shining light on them. See you in the next video.